Hello, welcome back. Talking today about the normal distribution. Normal distribution, great time. So we're going to be talking about this distribution over and over. Uh, we're going to start off with something called the standard normal distribution. What the heck is this thing? You've probably seen this thing before in psychology. Told you that IQ is normally distributed. Okay, maybe, kind of, in younger people. We're going to see that this normal distribution occurs all the time in natural measurements of like, you know, human characteristics, animal characteristics, things that result from a bunch of genes being like turned on and off. Um, and the combinations of those on and offs end up something like this normal distribution. I don't know. Imagine a Plinko board and the balls falling, and oh, well, if you drop them all in the middle, it's going to tend to fall in the middle because those left bumps and those right bumps are going to be, maybe average out, but some are going to go right all the time, some are going to go left all the time, and you get, something that looks like a normal distribution. Crude analogy for how the binomial distribution converges to the normal. I'll show you a video of that perhaps a little later. But this thing called the standard normal distribution shows up in things like height, uh, maybe weight. We've been told that IQ is normally distributed, and maybe, yeah, okay, cool. But this shows up in natural phenomenon all the time. Okay. Um, Standard normal distribution is the normal distribution n01. That's how we write it, with mean 0 and standard deviation 1. Okay, and we say if a variable x has any normal distribution, and we're going to write down normal distributions with the first thing being the mean. Mu here, sorry about the bell, is the mean, and sigma here is the standard deviation. Great. Um, Cool. We can standardize this. Z equals x minus mu over sigma, and we'll be talking about standard normal, standardizing or normalizing all the time. What does this do? This tells us again how many standard deviations above or below the mean. Great. So we're going to calculate z-scores. We have an interpretation of a z-score. How many standard deviations is this value above or below the mean? And now what I'm telling you is that we have a mathematical distribution right here. If you want to know what's the formula for this probability density function, that would be f of x equals 1 over square root 2 pi e to the negative 1/2 x squared. And if you're saying, oh, that looks like a fun thing to integrate, you're wrong. It's not. You got to do a polar transformation, or you got to do something goofy. But that right there, this is the function mathematically that describes this curve. We're not going to do anything with that. You're welcome. We're going to use, we could integrate that function to find probabilities, but it turns out we have a table that has already integrated this function for us that will find probabilities. If you don't know what integrated means, found the area under that curve. We're going to be talking about that a lot. And we're going to find out our calculator can also help us calculate these probabilities. So good news, you don't have to integrate that thing. If you want to, go for it. If you want to exercise in some calculus, go see how you can do that. So we're going to talk about standard normal distributions. Standard normal distributions is this right here. If I wanted to be pedantic, I'd probably change this to a z and put a z up here. And you can remember that z is x minus mu over sigma, so we can substitute that in there and do some more complicated calculus if you really want to, but we're not going to, so don't worry. So standard normal distribution, this is our focus for the day. How can we calculate probabilities for things that we're told are normally distributed? How can we do it quickly with maybe some sort of rule of thumb, and how can we do maybe more exactly with use of a calculator or use of our z-table. You'll need your formula sheet and your calculator, so pause and go get that if you don't have it already. So next thing we've got here is this thing called the empirical rule. What's an empirical rule? Empirical is what you observe, right? Empirical rule, this is going to be a rule of thumb for the normal distribution. right now, you don't have any idea what is reasonable under the normal distribution. You've never dealt with it before. You have no gut feeling for is that even an okay kind of answer at all? The empirical rule should kind of help you um, establish kind of a feel for this distribution. What's the idea here? In a standard normal distribution, we have this thing 68, 95, 99.7. 68% of the data is within one standard deviation. I'm saying right in here, that's 68%. 34 and 34 make 68. How do I know it's 34 on each side? It's symmetrical. Right out to the side, we've got very nice symmetry. Symmetry allows you to do some calculations here. You know, if you say, okay, well, if I'm right here, 50% below, 50% above, you know, you can do some neat things to make your life easier. They're not neat, but they make the calculations go quicker. 95% of the data is within 2 standard deviations. We're going to talk about 95% confidence intervals in this class. You see them in the media all the time. If you're looking at polling, you're looking at 80, 85, 95% confidence intervals. What does that mean? We'll talk about later. But you know, to do that, we need to look 2 standard deviations away, it turns out, from what we've been observing. So within 2 sigma, right here, you might have 95, and within 3 sigma, you'll see 99.7% of the data is within there. So how much of the data is outside 3 standard deviations? Well, if 99.7% is inside, that leaves 3% on the outside. We can use those sorts of ideas about the complement, something we'll talk about later. You talked about complementary angles before. We'll talk about complementary probabilities in this class. A similar sort of idea. We're not adding up to 90 degrees. We're adding up to 100%, but you know, you can follow that. So normal distributions, we can do some quick math. If we know the mean and the standard deviation, we can do some quick math with the empirical rule. So if we know mu and sigma, we know it's going to be this shape. We know about everything we can know about the normal distribution. So 2 things here. Well, let's take a look down below. First thing we're going to do is we're going to sketch one of these. We're going to be sketching these things all the time. It's the first step in a problem that asks you to find a probability with a normal distribution, is to sketch this thing out. So scores for high school seniors taking the verbal section of the SAT has a mean mu of 490 and a standard deviation sigma of 100. So I'm going to write this normal, mean of 490, standard deviation 100. I'm going to write below that mu and sigma. If you want to, practice making some mu's, make yourself some mu's. Give it a nice long tail at the beginning, and here's your sigmas. Great time. So mu's and sigmas, make the tail long and the mu and whatever. So 490 and 100. So we're saying, okay, what are we saying? Sketch this out. Oh, that's a pretty good one. Don't tell anybody. Put a little dash down the middle, and we say what's right there in the middle. There's 490. Great. That is the mean mu. And that has a z-score. Well, think about this question. Z-score is how many standard deviations away from the mean is the measurement. What's the z-score of the mean? What's the z-score of the mean? If you put mu into that formula, what do you get out for z? Mu minus mu over sigma. Mu minus mu is 0. So the z-score of the mean is 0. So I'm going to put 3 things here. The value, the symbol, and the z-score. I'm going to write that out to the side. Then I'm putting here the value, the symbol, and the z-score. Value, symbol, and z-score. And that's what I've written there. I've got 490, which is the value, mu, which is the symbol, and 0, which is the z-score. Go ahead and take a moment to, well, I'm going to do one more for you. We'll do mu plus 1 sigma and mu minus 1 sigma. We're going to find out that a standard deviation goes about to the inflection point, calculus people, of the graph. The inflection point where it changes from concave down to concave up. And you can see, if you draw it right, should be right about there. So we're going to say that to that inflection point, that's our good eyeball of how far away the standard deviation is. standard deviation. 1 standard deviation away is the inflection point. Okay, so you can estimate there. So we've got what do we have here? We have 590 and 390, and there's a 9 there, and that's mu plus sigma and mu minus sigma. Sorry, I've chose the bleedingest pen to do this. I'll use a pointier pen. So let's go ahead and pause, sketch this out 2 more standard deviations, and because this will get a little tedious. So sketch 2 more standard deviations to mu plus 2 sigma and mu plus 3 sigma. All right, so to save in the exercise and tedium from the video, I've skipped ahead and shown you from 190 to 790. Mu minus 3 sigma minus 2, 1, 0, 1, 2, 3. That is again z-scores of -3 to +3. Z-score is how many standard deviations away it is. So you'll notice the z-score is just the coefficient on sigma. 3 standard deviations away, z-score of 3. It's positive. 3 standard deviations below, z-score -3. Below. Great. So you can use that picture and the knowledge that 68, 95, and 99.7% of the data falls within 1, 2, and 3 standard deviations of mean. You can use those pieces of information to quickly estimate probabilities. So taking a look at the next page, you'll notice on the next page there's some questions. Let's take a moment to answer them. What percentage of the seniors scored between 390 and 590 on this SAT test? So we're going to write that as a probability statement. Probability X between 390 and 590. And we don't want to do any integrals. We just want to estimate this using our graph. You'll notice that 390, that's, what is that? That's mu minus sigma. 590, that's mu plus sigma. We're talking about things that are 1 standard deviation above and below the mean. Take a look back here. For this first probability, I'll use a color over here. We're talking about this region. Want to know what's this probability in here between 1 below and 1 above? Highlight this pink for you. What is that? Well, -1, +1, -1, +1, -1, +1, that's 68% of the data in there. So within 1 standard deviation, we can draw the picture for ourselves, 0.68. I can write that as 68%. It asks us for a percentage. Take a look at another one. One student scored 795 on this test. How did the student do compared to the rest of the scores? Well, where is that? That's somewhere up here. Well, if I know that 99.7% of the data is here, then that means 0.15% of the data is below it. So what is he? He's in the top 99.85%. So I could ask myself, maybe, what's the probability that someone scores less than 795? And you could say, well, it's at least 0.9985. That is 99.85% people score less. Cool. So the empirical rule lets us make kind of quick calculations. If we know the standard deviation, key is we know the standard deviation, and you'll notice all these problems have numbers that are like even numbers of standard deviations. That's 1 standard deviation below, that's 1 standard deviation above. This is approximately mu plus 3 sigma there. So it's nice round numbers of standard deviations. Last one, a rather exclusive university only admits students who are among the highest 16%. What score would a student need to get admitted? Well, top 16%. Well, what do you know? If 68 is within 1 standard deviation, 100 minus 68 is 32. And half of 32 is 16. So what do we know? We know up here is 16% of the data. We know that above 1 standard deviation from the mean, that's 16% of the data. So what do you got to get? You got to get above a 590. So that's nice. The empirical rule can let us do, okay, 68% was within 1. If 68 is within 1, 32% is outside 1. If 95% is within 2, then 5% is outside of 2. If 99.7% is within 3, then 0.3% is outside. Okay, so you can do some quick math with the empirical rule. Get your calculators out. Get your calculators out. It's calculator time. We can find areas under normal density curves with our calculator. And you've got some steps here. So first, check that your data is approximately normal. Great. With no outliers, you can make a box plot or a histogram. We're going to see later that you can also make something called an NP plot, but AP's really gone away from this. Draw and label a density curve with the given information. The minimum value, the maximum value, the mean, the standard deviation. And show the shaded area. We are always going to be shading in here. Need to draw a picture. Say, okay, here's the mean, here's a standard deviation, and I want to find this area in here between the minimum value and the maximum value. You need to label something like that every time. Need to define your x variable and set up your probability formula. Defining your variable, both mathematically and in context. Math and context. And then we'll set up a probability formula, and then we'll do the steps in our calculator. When you do normal CDF, if you write this down, you need to label all this stuff. We're going to always be labeling our calculator statements in here. Label your calculator work. I'm going to write that up the side real big. Label your calculator work every time. You can get away with it in here. It's not as bad as calculus. Calculus. I don't think you ever wrote anything down from the calculator. You can write stuff down from your calculator in here if it comes about. So each full carton of grade A eggs, great, consists of 1 randomly selected empty cardboard container and 12 randomly selected eggs. All right, the weights of such full cartons are approximately normally distributed with a mean of 840 and a standard deviation of 7.9. What is the probability that a randomly selected full carton of grade A eggs will weigh more than 850 grams? Circle that word more. So let's define some stuff. Let's say that X is the weight of a full carton. And we know that X's are distributed normally with a mean of 840 and a standard deviation of 7.9. Cool. We're told it was approximately normal, so we don't have to do that. Draw and label a density curve. Let's do that. We are told, well, that's a pretty good one right there, that the mean is 840 and a standard deviation of 7.9. Okay, we need to find 850. So 850 is somewhere like up here. And we want to find the area greater than it. So that's all the picture I would need to show. I've labeled the mean, I've labeled the standard deviation, I've told you over here it's normally distributed. That's a good start. Need to see that every time. You can do that without you can do that without getting any numbers, and that's like half the credit. So please do that for me. Define your variable, state it in terms of a normal distribution, or if it's a different distribution, we'll talk about that later, and give me a little picture. More. Above, right? So we're looking here for the probability that X is greater than 850. We're going to find that in our calculator using this thing called the normal CDF. What does that stand for? That's the cumulative distribution, or distribution function. How much of the data is accounted for up to here? it's integrating. What is it doing? It's integrating that function from earlier between your lower and your upper bound, right? It's doing this. 1 over square root of 2 pi sigma squared e to the negative 1/2 x minus mu over sigma quantity squared dx. It's doing that. Do you want to do that? No, it's gross. You don't want to do that. We're going to let our calculator do that, or we're going to look at a table of values that have done that over and over for different z-scores. So we've got our probability statement here. Don't worry about the calculus. You don't have to do it. Just throw it there for the calculus people, because it will show up later maybe in college. We want to find this probability. We're going to use this normal CDF function. We're going to type in some things into it. We're going to type in its lower bound. What's the lower bound? We're looking for values that are 850 and up. I can't put infinity into my calculator, so I just put a bunch of 9s. Just spam the 9 button. So this is lower bound, this is the upper bound, and this is our attempt at infinity. The mean is 840. The standard deviation is 7.9. So I'm going to label, sorry that 9 got a little goofy, the lower bound, the upper bound, the mean, the standard deviation. I'm going to label that every time. Let's put it in our calculator. 42, that's the answer. Okay. So what are we going to do? Where is this thing? It's stat. Go over. Second. It's not in stat. God, what am I doing? Hit second. Quit out of there. Second vars is going to get your distribution menu. Go down to normal CDF. The steps are above. The lower bound's 850. Upper bound, spam the 9 button. Mean is 840. Standard deviation is 7.9. It's gonna find us this probability for us. What is the probability? 10%. Okay. Is that reasonable? Well, yeah, that's kind of reasonable. 0.1028 is what we're gonna write down. Oh, what the heck happened there? It's like I had a small stroke. 0.1028. All right, so there's our probability. Why is that reasonable? Well, think about this. You knew that 68% was going to be within 1 standard deviation. It's the empirical rule. 68 was within 1, so 32 is on either, is the combined total outside. Half of 32 is 16, so there's got to be less than 16% up there. And that sure is a value less than 16%. Use your empirical rule to say, is that reasonable? Empirical rule told me it was going to be less than 16%. I got a value a little less than 16%. Seems reasonable. You need to use the empirical rule to assess reasonability. There you go. Empirical rule is also going to show up in multiple choice questions. Question on the next page about some melons. What's the probability a melon will have a diameter greater than 1/37? You try it. Set up a probability statement just like I did in the last page. We're going to pause. We're going to look at the answer key because I don't want to do this one for you. You stopped and paused, right? Please do it. So you do this, and you could either set up a z-score. You probably didn't do it this way. You probably got an answer of, hopefully got an answer close to 0.2119. How would you have done it in your calculator? Well, there's your upper bound, or excuse me, there's your lower bound, upper bound, there's your mean, and there's your standard deviation. You'll see on the calculator. Let's switch over and do it on the calculator. Oh, that's not the video camera you wanted to see. Sorry, messing it up. What a shame. I've had such good quality video until now. So you're going to do normal CDF. You're going to put in your lower bound, which is 137. Your upper bound, which you're going to spam the 9 button on. Your mean, which is 130. Hopefully I typed that in. Oh, no, it's 133. And a standard deviation of 5. And you're going to hit enter on that, and you're going to get that same answer that the scoring key gave you. Let's keep going. You can find this stuff in your calculator. So you can go one way in your calculator. You can find probabilities. Oh, that's so bright. calm down there. You can go the other way and find a value given an area or a percentile, right? So you know, okay, z equals x minus mu over sigma. And if we know either z, if we know z, we can find a percentile. But it turns out if we know a percentile, we can find a z. It's a one-to-one mapping between something z-score and the percentile of values less than it. And we haven't done it yet, but we got a table that tells us the percentile, or the percent of values that are less than a given value. And the calculator knows these values too, so it can go back and forth between them. All right, we're going back and forth between z-scores and percentiles. And what's the function in our calculator that does this? Not surprisingly, inverse norm. If the norm CDF goes this way, left to right, inverse norm goes right to left. And we can switch between these two things. What does inverse norm have? Inverse norm takes the percent falling below the mean, the standard deviation, and finds the value. What does that look like? Graduating seniors at a certain high school with GPAs in the top 20% are eligible for special scholarships. Great, top 20%. Grade point average for seniors that are at that high school are normally distributed with a mean of 2.35 and a standard deviation of 0.55. What's the minimum GPA that somebody must have in order to qualify? Okay, what do we know? Take what you know and draw yourself a picture. That was not as good as those past ones. We know the mean is 2.35. We know the standard deviation is 0.55. So what is that? One standard deviation above, that's like 2.9 or something. Okay, one standard deviation below, that's like, what is that? 1.8 or something. I think that's right. So what do we want to say? Where's the top 20%? Well, I know that's 16% from the empirical rule. So somewhere over here is the top 20%. But notice that this function finds below areas. So what's the area below? If 20% is above, we want to find the place where 80% Christmas colors is below. But the question is, what is that x value below which 80% of the scores fall? We can find that with the inverse normal distribution. Inverse norm, we're looking for the place below which 80% of scores fall, and I'm going to write that as percentile, percent below. The mean is 2.35, standard deviation of 0.55. What's that going to be? In our calculator, you go second vars, gets you your distribution, inverse norm, area 0.80, it's always area below. If you have a new calculator, you might have the option to choose like left areas, right areas, and center areas. If you don't, it's always left. Talk to me if you have those options or getting confused. 2.35, 0.55, paste, enter. We're talking about a GPA above 2.81, which makes sense. The picture had it a little less than 2.9. Empirical rule helping us out yet again. So I'm going to pause. I need a drink. All right, so back to it. What's the idea here? This inverse norm function, what do we got here? We can have values and z-scores. And we've got, again, percentiles, percents less than. We've got a function that takes us from values to percentiles, and we've got a function that takes us back. We've got the normal CDF that takes us between values and z-scores to percentiles, and we've got the inverse normal function that takes us from percentiles back to values and z-scores. Nice to know that. That's an important kind of visual representation of what we're doing right now. According to a website, great. That sounds legit. The heights of 3-year-old females are approximately normally distributed with a mean of 94.5 and a standard deviation of 4. All right, so I might say X 3-year-old female heights, and I might say that X is distributed normally with a mean of 94.5, that's mu, and 4, that's your sigma. That's how we write that. X is distributed normally with a mean of 94.5 and a standard deviation of 4. Got to be able to pronounce that kind of stuff. Turn those symbols into thoughts. What is the third quartile of this distribution? Third quartile, that is the 75th percentile. So what are we looking for? We're looking for the place below which 75% of scores fall. How are we going to find that? We're going to find that with the inverse norm function. Area 0.75, mean 94.5, standard deviation 4, mu, sigma. Make sure you're labeling all that. Go ahead, take your calculator. Second vars gets you your distribution menu. Notice above vars, DISTR, distribution. Inverse norm, 0.75. What is this? 94.5, 4. Paste, paste. Oh, what'd I do? Had a bad area. Can't put an area greater than 1 into the inverse norm function. The domain of areas is from 0 to 1. So if you've got an area greater than that, it's gonna take a dump on you. 97 point, we'll call it 97.2. That is the height below which 3/4 of heights fall. Great. I'm gonna leave it at that. The rest of these, it's just a repetition, changing the areas over and over. Take a moment, check the key. Looking at your key, inverse norm functions, well labeled for you. Notice for a symmetric distribution, the 50th percentile, that's just the mean. It's whatever the 94.5 they gave you. And do some more for CDC. This is beating inverse norm to death. I didn't feel like I needed to walk through all 5 of these. What I am going to walk you through is how to use the z-table. So let's go back and look at that. So we've been talking about percentiles and z-scores, and the z-table, which is in the back of your book, it's called Table A on your formula sheet. This is just, it's a before everyone had these dang computers in their pocket, they had to carry around a table of integrals with them. That's what this is. Somebody sat around and found a bunch of areas over and over. And these give the probability that it takes a z-score less than some z-score. And what do we got on the outside of this table? We got what is the z-score on the outside, and table entry for z is the probability lying, but this is a probability that takes a value below. We got a bunch of probabilities. And notice the probability it takes a value less than a z-score of 0.0. What is the z-score of 0? It means we're 0 standard deviations from the mean. That means it is the mean. The probability you take a value less than the mean is 50%. Oh, hot dang. That's nice. You notice the further you get away, very negative z-scores have much smaller probabilities. And the most positive z-scores, z that is 3.4 above the mean, it's a very high value. So as we go up in z-score, we get higher above the mean. We're accounting for more of the values, not surprisingly. So this table, just as the norm CDF let us go from z-scores to probabilities, the z-table lets us go from z-scores on the outside to probabilities on the inside. Conversely, we can go from the inside to the percentile. Ooh, look at that right here. Where's that guy? 75th percentile is right about there, goes along with a z-score of 0.68 or whatever out there. So we can use this table much like we use the inverse norm and norm CDFs. So what is this with an analogy? This going from z to the percentile, that's what the norm CDF does. Going for the percentile back out to the z, that's what inverse norm does. And we can do that here. So if you wanted to find the probability something took a z-score below 0.81, well, you'd say, okay, where's the positive z-scores? Right here. Z-score 0.81, here's 0.8. Here's 0.01. 0.81 has a probability below of 0.7910, which is what the notes show us. So if we wanted to find the z-score for the median, again, the median is, what are we looking for? That's the mean. Well, that's the 50th percentile, 0.5000. Oh, what is that? Oh, we already found it. It's a z-score of 0. We're talking about their z-score of 0. If I want to find the first quartile, that's 0.2500. I'm going to find the percentile in the table closest to 0.2500. That's going to be below the mean. Take a look at your negative z-scores. Where's 25%? 23%, 27%, 25% is somewhere between these two. Somewhere between negative 0.67 and 68. Let's call it negative 0.675. And similarly, we're looking for the third quartile, that's 0.7500. That's a z-score of positive 0.675. How did I know that so quick? It's a symmetrical distribution. So if I know the place where 25% is less than, with a little symmetry, I can find the place where 25% is greater than. Again, 0.6768, split the difference, call it 0.675. So let's do some work with the z-scores here. In the United States, egg sizes are set by the Department of Agriculture. Okay, and we say what a large egg is. It's between 57 and 64, excuse me, 57 and 64 grams. Suppose the weights of eggs produced by hens owned by a particular farmer are normally distributed with a mean of 55.8. Cool. If 20% of the eggs from these hens are extra large, greater than 64, what is, oh, I gotta solve for the standard deviation? Oh, solve for sigma. So I need an equation that has sigma in it. Ooh. Z-score formula. Okay, what is the standard deviation of weights of eggs from these hens? 20% are extra large, okay, greater than 64 grams. What do I know? Okay, so for A, what do I know? I know that the mean is 55.8, and I know that 20%, that's like right here, 20%, 0.20, and I want to know what's that value. Okay, all right, how do I know enough? How can I know enough? Well, I know z equals x minus mu over sigma, and I know sigma, but excuse me, I don't know. So I'm trying to solve for this. What do I know? Well, I know the mean. I know the mean is 55.8. Do I know? I don't. Do I know x? I don't know x. What do I know? How can I do this? What am I trying to do here? Pause and think about it for a moment. What else do we know? I haven't given you everything. We do know x. We do know x, guys. X is 64. What do we not know? We don't know sigma. What is this sigma? So x is 64. Great. I don't know sigma. How do I know? How do I know z? I can find the z-score associated with the 20th percentile. Take a look over here. 20th percentile. What is the z-score associated with the 20th percentile? 20%. That's a z-score of negative 0.84. Ooh. Negative 0.84. Okay. I know enough. Negative 0.84 equals 64 minus 55.8 over sigma. Can you do a little algebra to solve for sigma? Do it. I messed something up. I look for the place where 20% was less than. 20% greater than needs to be positive. Sorry. Fix that. I'll do this algebra for you from here. That's going to be 64 minus 55.8 divided by 0.84 positive, and you're going to get z-score 9.76. Excuse me, not z-score, but sigma equals 9.76 grams. Based on your answer from part A, what percent of eggs from these hens are large? I'm looking for the probability that it takes a value between 57 and 64. And now I know everything I can about x. X is distributed normally with a mean of 55.8 and a standard deviation of 9.76 mu sigma. Okay, and if I wanted to find those, I could use normal CDF, and that'd be fine. I have a lower bound, I have an upper bound. Or you could use z-scores. You tell me which is easier. I could convert these into z-scores. Probability z is between 57 minus 55.8 over 9.76. You can see that this is cumbersome. 64 minus 55.8 divided by 9.76. Okay, and I can convert these to z-scores. I already know the top one. The top one I already found is 0.84. The bottom ones, that's just from above. It's the same numbers. 57 minus 55.8 divide, don't do that. That's bad order of operations. Divided by 9.76 is a z-score of, what is that? 1.2, what do we got? Let's call it 1.2. Excuse me, 0.12. So we can convert those to z-scores, and then, well, how are we asking for there? We're asking for the probability between like here and here. That's the worst one I've drawn today. We're asking for like that probability between 0.12 and 0.84. But the problem is that this picture, it only gives us less, it doesn't give us betweens. So how are we going to find between if we got two less thans? We're going to do the big one minus the small one. To find this area, the in-between area, I'm going to take the big less than minus the small less than to give me the in-betweens. Let's show that up here. To find this, it's going to be the probability that z is less than 0.84 minus the probability that z is less than 0.12. Doing that, 0.84 is 0.7995. 0.12 0.5478. Subtract those. And we've got our answer, about 25% of eggs. Great. So, would you have wanted to use z-scores there? I mean, so up top, you had to use the z-score formula. There's no other way to solve for sigma up there. But down at the bottom, good God, I'd want to use a norm CDF. Norm CDF is way easier than this. Way easier. So if you're given mu and sigma, you should probably use norm CDF. You can see how this is much quicker on the bottom. The top, you got to use the z-score formula. Last thing I've got for you, how do you know if data is normal? The answer to that is to graph it. Look for a histogram, no strong skew, no outliers. I'm not going to take the time to type this in your calculator, and I'm actually going to look at the key for this, make a histogram, say, is it close to normal, or does it show skew? If there's no strong skew or outliers, you can say it's approximately normal. We're going to use this word approximately all the dang time. Down for normal probability plots. A normal probability plot shows, well, if it's a straight line and it doesn't have skew and it's equally spread out with no outliers, then you can say it's approximately normal. I'm gonna go ahead and cross this out. This never shows up, and I'm not worried about it. You don't worry about it. If you have a question over normal probability plots in the homework, skip it. Do though make a histogram of the data. Make a histogram of the data, put that in your calculator. We're going to look at that in a moment, but I want to spend more time talking about normality. It's hard to say whether data follows that very specific formula. It's hard to say with your eyeball. So what I need you to do, and you've seen the funny cartoon, you need to say something's roughly, approximately normal. We don't need to say something exactly normal. We need to say it's approximately normal. So take a moment to put that data in your calculator. Make a histogram. If you don't remember how, now's a good time to practice. Ask me in class. And then let's assess normality. So you put that in your calculator. You got that histogram. Maybe you didn't get that histogram. Maybe you got a different histogram. Really depends on how you set things up in your calculator. But is that skewed? There's no strong skew. There's no outliers. I need you to add something if you're gonna ever write something like this. There's no strong skew and there's no outliers. So we can say that the distribution of usable capacity in these refrigerators, man, that's a weird word, is approximately normal. Please add that. So we can say that the distribution of usual capacity in these refrigerators is approximately normal. We are going to be using that word approximately all the dang time. So that is it for 2.2. The 2.2 homework is important and challenging, and if you wait until a week after this lecture to start it, you are hurting yourself because you need to do this lecture soon. You need to start this homework soon because it's challenging, and you're going to have questions for me. Good luck, Godspeed. We'll start chapter 5 next time.